So what if an AI could get better at coding, not by learning from us, but by, well, by teaching itself? We're about to dive into a really groundbreaking new paper on a method called self-play for software engineering with reinforcement learning, or SSR for short. And look, this isn't just about fixing bugs a little faster. This is a huge potential leap towards software that's truly autonomous and maybe even super intelligent. Let's get right into it.
I mean, really think about that question for a second. Imagine an AI that isn't just stuck learning from human examples. Instead, it creates its own programming puzzles and its own solutions, getting smarter and smarter in this amazing feedback loop. We're talking about a system that could, in theory, blow past the skills of any human programmer out there. That's the revolutionary idea we're digging into today.
So here's our game plan. First, we'll talk about the human bottleneck that's holding current AI back. Then, we'll get into the self-play revolution that just might shatter it. We're going to spend most of our time on the really cool part, how SSR actually works, the nuts and bolts. After that, we'll look at the jaw-dropping results, and then we'll wrap up by dreaming a little about the future this could all unlock. All right, let's kick things off with our first section, AI's human bottleneck. This right here is the fundamental reason why even our best and brightest AI models today just hit a hard ceiling on what they can do. See, here's the problem. AI learns from data we make. It's sifting through millions of our GitHub issues, our bug reports, our code fixes. And yeah, that's powerful, but it means the AI is totally trapped inside the box of human knowledge. It's learning our way of solving problems, our patterns, and yeah, even our bad habits. How could it possibly come up with a solution that no human has ever even considered? It's literally impossible with this method. So how in the world do you break out of that box? Well, that brings us right to section 2, the self-play revolution. This is a massive shift in thinking, from learning by copying us to learning by doing it all on its own. And the absolute best way to think about this is AlphaGo. Remember that? It didn't become the world's greatest Go player by studying ancient human masters. No way. It got there by playing millions upon millions of games against itself, discovering strategies and moves that humans literally never dreamed of. SSR takes that exact same, incredibly powerful concept and just applies it to writing code.
Okay, so this all sounds amazing, but how does it actually work under the hood? It's time to get into the nitty-gritty, the mechanics of this SSR engine. This is where we see how that self-improvement loop really gets going.
At its heart, and this is the really elegant part, it's all driven by a single AI model. But it kind of splits its personality in two. It takes on two totally different roles, and it's essentially just having a conversation with itself. One side creates a problem, and the other side has to solve it. It's this constant back and forth that creates all the learning. First up, you've got the bug injection agent. You can think of this one as the mischievous sparring partner. Its whole job is to go into a real-world code base, find a weak spot, and then strategically plant a really tricky, realistic bug. It's basically creating the perfect homework problem for its other half. So yeah, this first agent basically pops in and says, all right, I'm going to break this, but I'm going to do it in a really clever way. You know, this isn't just random chaos. It's a carefully calculated move designed to be a tough but solvable learning experience. And that, of course, brings us to the second role, the bug-solving agent. This is the other side of that same coin. Its mission is to take the broken code, figure out what its partner just did, and write the perfect lines of code to patch it all up. Now, what's really important here is that the solver agent gets 0 hints. There's no human-written bug report saying, hey, the user login is broken. Nope. It just gets a piece of code that doesn't work and a failing test. And from that alone, it has to figure everything out. It's like, all right, you broke it. Challenge accepted. So how does that handoff actually work? The bug injector bundles everything up into what it calls a bug artifact. This is the formal problem description. Let's walk through it real quick. TestScript.sh is simple. It's just how you run the tests to see if you fixed it. TestFiles.txt is actually a clever anti-cheating device, so the solver can't just delete the test and claim victory. TestParser.py helps it understand the test results. Now, BugInject.diff, that's the real problem, the exact lines of code that created the bug. And finally, my favorite, TestWeaken.diff. This part is brilliant. It actually changes the existing tests to hide the bug, just like subtle bugs sneak past us in the real world. This whole package makes for an incredibly realistic challenge. But what happens when the solver messes up, when it fails to fix the bug? Oh, this is where the system's genius really shines. A failed attempt isn't just tossed out. No,
The broken fix itself gets packaged up as a brand new, even harder problem, a higher-order bug. It's like the AI is saying, okay, not only did you not fix my bug, but your terrible attempt created a new one. Now go solve that. This automatically creates a difficulty curve that's always pushing the agent right to the edge of what it can do. It's incredible.
Okay, so that all sounds incredible in theory, right? But does it actually work? Let's get to the fun part. Section 4. Let's see how this self-play idea actually stacks up against old-school training on human data.
The results are frankly staggering. On the SWE Bench Verified benchmark, which is a pretty standard way to test these agents, the SSR model improved performance by over 10.4 points. Now, in the world of AI benchmarks, that isn't just a little bump. That is a massive leap forward. And it wasn't a fluke. They threw an even harder test at it, the SWE Bench Pro, and it still got a 7.8-point gain. This proves that the skills it's learning aren't just for toy problems. They actually work on complex, messy, real-world software challenges.
So the takeaway here is just crystal clear. When you put the two methods side by side, the agent that was trained on its own self-generated problems consistently and significantly beat the agent trained on the best human data we have. Let that sink in for a second. The AI learned more effectively by talking to itself than it did by listening to all of us.
And all of this leads us to our final and maybe most important section, the future of superintelligent software. What does all this mean? What are the really profound implications of an AI that can teach itself to be a better coder than we are? Look, this isn't just some small improvement. It's a potential paradigm shift for how software is made. This paper points to a future where AI agents don't just help us, they could actually surpass us. Just imagine agents that can autonomously roam GitHub, learning and improving on a scale that no human team could ever hope to match. This goes so far beyond just fixing bugs. This is the path to AI that can refactor, optimize, and even architect brand new systems completely on its own. This is the moment software could truly begin to evolve.
Phew, okay, that was a pretty intense download, right? Brain workout officially complete. Let's just take a quick breath for a cool down.
And hey, if you enjoyed getting this deep into the future of tech, do me a huge favor and hit that subscribe button for Vibe Doc. Seriously, it's just one click for you, but it's a giant leap for the channels. Well, for the vibes. We'd love to have you around here more often.
So I'll just leave you with this final thought. Based on research like this, the real question doesn't seem to be if software will start to control its own evolution anymore, but when. Thanks so much for watching.